All right, so let's turn to page 1.1 of the reader. Okay. And I'll begin with the most basic element that's used in structural analysis. And we'll develop a so-called bar or a truss element. Okay, so the word element or structural member will be used interchangeably. Okay, and what we'll do is we'll take the differential equation approach. Okay, so I'll show you what the underlying differential equation is, what the unknowns are, what the boundary conditions are, and then we'll build this up into, from basic definitions, okay, all the way to what the structural element looks like in practice. Okay. So as with everything in this course, right, we're going to consider a one-dimensional element. Okay. Looks like this, so it's much longer in one dimension than in the remaining two. Okay. The endpoints of the element I will denote as nodes. Okay, and I'm going to call this a generic node I. This is going to be a node J. Okay, node. Okay, and what we'll do is we'll restrain this guy. Okay, put it on a so-called pin connection. It's not allowed to move. Okay, and then we'll put this guy on the roller like this. Okay, it can move up and can move to the left and to the right. Okay, so then, right, I'm going to assume that this bar is made of some elastic material. Okay, I'm going to put this on align it with the axis X. Okay, and corresponding to the nodes, I'm going to have outward directed forces, okay, acting on the nodes. Okay, this will be Nj, this one will be Ni. Okay, so Ni and J will be our nodal forces. Okay, and then I will allow a distribution of what's called the axial force, okay, with the axial load. So I'm going to denote this guy W. I'm going to make this a function of x, right? By the way, here x equals to 0. Here x will equal to L. Okay, where L is going to be the length of the bar. Okay. And I'm going to subject it to a distributed load, W. Okay. So W of x, right? So again, pay attention. Doesn't have to be constant. Okay, it can be any distributed load. I'll call it distributed force per unit length of the bar. Okay, we'll do it this way. Okay, so that's our situation. Okay, and under this set of boundary conditions, right, and this set of loads, I'd like to know how the bar displaces. Okay. For this, I will develop a differential equation. Okay. So how do we develop differential equations? Okay, I'm sure you've seen it in some of the classes, right? But in the context of mechanics, right, what you would do is you would zoom in, okay, at a given location x. Okay. You take an infinitesimal piece of the bar. Okay, so this coordinate is x, right? This is going to be x plus dx, okay, where dx is small, okay, much less than any sort of let's say measurable unit. Okay, and then you would zoom into this piece here and look at what's happening with a force balance. Okay. So let's see. This is our piece now. It's of size dx. Okay. I'm going to have some distributed load acting on it, Wx, right? And we're going to cut out this piece from the middle of the bar, right? So as a result, there will be a force on the cross section, okay? Right? The orientation of the force is always in the direction of the normal vector to the cross section. Okay, so this is going to be our n force, right? And on this side, we're going to have n plus some dn, okay? So as n changes going from there to there, right, that change is precisely denoted by dn here. Okay? And so this is what each infinitesimal piece of the bar looks like, okay? And then, okay, supposedly we'll put it on a pin and a roller like this. We'll apply distributed load, okay? The bar will undergo some deformation, okay? And not only are we going to see the node J move, right? We're going to see the particles along the bar move, okay? So in principle, at every location x, right, you're going to see a bar displacement. Okay? So we're not only interested in displacement at J, okay? We're interested in displacement everywhere. But then once you applied the loads, the bar has displaced, it has to be in static equilibrium. Okay? And not only the whole bar needs to be in static equilibrium, right? Every piece by piece like this, right? Every infinitesimal cross-section, right? If you go in and zoom in on the n and n plus delta n like this, right? Each one of those needs to be in static equilibrium. Okay? So what does that mean? Static equilibrium implies, right, that I'm going to take in the picture, right, and I'm going to sum all the forces together. Okay? And the end result must be zero. Okay? If it's not zero, then the bar is going to want to move more. Okay? There's no dynamics in this problem. If there's dynamics, there'll be some acceleration. Okay? But here, all the forces need to equilibrate. Okay? So what you remember from engine 30 and 310, right? Then sum of some forces in the x direction equal to zero, right? So what does that look like for this bar? Okay, well, I see three forces, right? N acting on the left side, n plus delta n acting on the right side, right? And then some cumulative effect of W. Okay? So mathematically, we express as it follows, right? Minus n, right? See, n is pointing in the negative direction, so it has to come in with a minus, okay? Plus n plus dn, okay, force coming from here, okay? And finally, plus, right, I'm going to take W of x, okay, and multiply it by dx, okay? This is sort of the first order approximation of the total force, right, acting on the specimen, okay? And then I'll set the end result to zero. Okay, so I can rearrange terms. Okay, and what I see is n is going to go and cancel minus n. Right? Yeah. Right. I can take this dx and divide the whole equation through by dx. Okay, and I get the following: dn, right, the increment of the axial force, divided by the size, right, of the infinitesimal element of the bar, equates to the value, right, of the distributed force in the x direction at the location x. Okay? And so then I can pass to the limit dx going to zero, right? And what happens is, right, instead of working with the quantities dn and dx, we're actually getting a derivative here. Okay, so in the limit as x goes to zero, this becomes first derivative of n, right, axial force, with respect to x, right, current position. And so this is a kind of differential form, right, differential equation form of the force balance, right? And the key is that, if you look back at this plot, right, this x was chosen in an arbitrary fashion, okay? So I can go and pick an x here. I get the infinitesimal piece of the bar. I run the analysis where I send d dx to 0, and I can, in principle, do it at every point along the bar, okay? And so the static equilibrium, as you've seen it in classes like Engine 30, where you have a sum of discrete forces that go to 0, right, is in this case where we're talking about quantities that are distributed along the lengths, right, is re-expressed in terms of a differential equation statement like this. Okay? So it's a differential equation of the force balance, and the point is holds at every point along the bar. Okay, it's very important. So I think we need to start getting used to the fact that we'll be working with quantities that are distributed, okay, over the domain. And in that case, these sort of simple discrete force equilibria don't work anymore. You need to use a richer description, other kind of language, and we're going to be using the language of differential equations to do this. Okay? So very powerful. Okay? Good. All right. So now, if you look at this situation, right, for example, you're trying to solve this problem, right, as a boundary value problem, okay? For now, you've expressed your equations in terms of n, okay? Now, when you think about differential equations, you need to think of boundary conditions, okay? And you don't really, by looking at a setup like this, right, you know that the node on the left is restrained, for example, right? So it means that it doesn't move, right? The displacement is 0, right? However, you don't necessarily know what the force is, okay? The force will come out of this sort of equilibrium type calculation. And so what I'm trying to tell you is writing down differential equations in terms of force type quantities, okay, is not a good idea, okay? So you need to do something else, okay? So keeping forces, okay, distributed as unknowns, as unknown function is not practical. Okay, so it boils down to basically boundary conditions. Okay, another thing in multiple dimensions also doesn't work. Okay, so what you need to do is rewrite the differential equation, right? In terms of quantities that you can prescribe. The boundaries. Okay. Okay. And so for this reason, there are a couple more steps that you need to take, and I believe you've seen these things in 310, so let me remind you. Okay? So you need to add what's called a constitutive law. Okay? And what constitutive laws do, right, they relate force or stress type quantities to kinematic quantities, okay? Displacements, strains, so forth. Okay? And so the way this proceeds here, okay, is first you write down n, as a function of x, okay? So distributed force, okay, equals 2. Right? So if you look at the cross-section of that bar, okay, could be geometrically complicated cross-section, right? Then you have something called stress, right, on that bar. Sigma, okay? Stress, or force per unit area. And so then you can express the force as A is a function of x times sigma, right, is a function of x. This is stress. This is the cross-sectional area, okay, A. And again, the interesting thing here is as you move along the x-axis, the stress can change, so can the area, right? So you don't necessarily need to work with the bars of the same cross-sectional area. This can change, although most cases we'll look at A will be constant. Okay? And then you go back, right, and you invoke what you know from 310, okay, a relationship called Hooke's law. Where you say, I'm going to have my stress as a function of x to be proportional to the strain as a function of x, okay? This is strain. And the two are related through a quantity that's experimentally measured, E. Okay? E is a so-called elastic or Young's modulus. Okay, so this is sort of the simplest. This is the simplest expression that's used in mechanics of materials, right? It's applicable in a sort of very small sort of deformation regime, but that's where we are going to focus on in this class. Okay, of course, there are materials and structures behave in a much more complicated fashion, and there are different constitutive laws that are out there, but that's the constitutive law that we'll use in this course. Okay, this is our constitutive law. Okay, but then again, I don't want to write anything in terms of strains, right? In fact, I'd like to write things in terms of displacements. Okay, so the last ingredient I need to bring in is a so-called compatibility. Okay. And compatibility in this case is the relation between displacements and strains. Okay, and so just let me illustrate something. Okay, supposedly you have a bar. This is of size L. Okay, and just say, for the sake of the argument, right, you've prescribed this displacement to be 0, right, it's fixed, and then you go, okay, and you move this end by another L, okay, right, and so then what happens is the bar elongates, develops a significant tensile force, right, and goes from L to the size 2L. Okay? So doubles in dimension. Okay? Then supposedly on the other side you had a bar, prescribe it here, right? It is of size 2L. Okay? And then you go and you displace it, okay? And now you displace it also by 2L, okay? And so in this case, as you've learned in your previous classes, right, if you look at the strain, right, what do you need? You want the new size, right, the deformed size over the original size, right? So in this case, becomes 2L over L, okay, equals to 2. Else cancel out, right? Same here, right? If you look at epsilon, Okay. Here, the new size is you start with 2L, you add 2L, you get 4L, and you divide by the original size, which is 2L. L's cancel out. 4 over 2 is exactly 2. Okay? So you see what I mean? It took a different amount of displacement, in this case L, and in this case 2L, right, to develop the same strain. Right? Right? And so as a result, if the relationships, right, if we apply the constitutive law, okay, at the level of stresses and strains, right, but if we'd like to bring in displacements into the picture, okay, we need to develop a relationship, right, between displacements and strains. Because in that case, right, if the bar is made of the same material, and just for the sake of argument, say the Hooke's law applies, right, because the strain here and here is the same, right, the stresses here and here will be the same. However, it takes a different amount of displacement, okay, to get the same stress, which relates to the fact that the size of the original bars are different, okay. And so then what you want to do, right, is you want to express the strain, right, in terms of displacements. Okay, so let U denote the displacement. Okay, specifically axial displacement, and U is a function of x in this case, right? Then, as you've seen in 310, epsilon can be defined as the rate of change of U with respect to x. Okay, U has dimensions of length, x has dimensions of length, and your strains are not non-dimensional. Okay. So again, the way you see this, right, is if you take a look at the original bar, right, 0 to L, you take an infinitesimal piece, right, say x, and this is x plus dx, right? You've applied some force to this guy, right? You've developed a displacement field, which is here u of x, and here is u of x plus du, right, of x, okay? And so the new the elongation, right, of the bar becomes u of x plus du, right, as a function of x, minus u of x, okay, and then divide by the length, original length, which is dx, okay. U's cancel out, and you get du dx, you see, as applied at the infinitesimal level. And so this is how the strain expressions are derived. So this becomes epsilon. Okay. Good. So our compatibility states that epsilon of x, right, at every point is going to be different, is obtained by taking u, right, the displacement at every point along the bar in the axial direction, think of it as a function of x, and differentiating with respect to x. This is a derivative. Okay, all right. So now let's put everything together, right? So take problem differential equation, which is written in terms of n, right? Let's take the constitutive law, and let's take compatibility. Okay, and let's apply them all together. Okay, apply all together. the end result is the following differential equation. d dx of E, right? A could be a function of x times du dx, right, equals to minus w applied in the x direction as a function of x, right? So let's see. You get du dx, that's your epsilon, right? Epsilon goes and hooks up with E, right, to give you the stress, okay? The stress hooks up with A to give you the N, right, the force. And then from the problem differential equation, we know that the rate of change of the force is the negative of the applied distributed load. Okay? And so that is the equation that is of interest in this work. Okay? So for every applied distributed load, okay, given the problem material parameters for the bar, right, and the bar geometric parameters, okay, I'm going to find my axial displacement u that satisfies this relation and the boundary conditions. Okay? So an important special case is E and A constant. Okay. In this case, the bar is referred to as a prismatic bar. Okay. And then the differential equation simplifies to this. EA d squared u dx squared equals minus w of x. Okay. Good. All right. And so let's see, where do we go from here? Okay. dx, I apologize, dx squared, like this. Okay. This is the equation for the prismatic bar. Okay. So then the way solutions are generated for this case, okay, and again, I can only say a few general things, and then we have to take different cases and see what happens, right? But the way you construct the solution, right, and if you've seen, you've taken courses on ordinary differential equations, right, through the math department here, right? So when you deal with boundary value problems, is you look at u of x, right, as something that's being composed of two parts, uh of x and up of x. Okay, this guy is referred to as a homogeneous solution. Okay, this guy is a particular solution. Okay, and so UH is basically right, comes from solving ddx right, EA du dx, okay, equals to 0, okay, without forcing or boundary conditions. Okay, kind of, if you're more sort of math oriented, you're basically finding a non-trivial expression, right, for the displacement, okay, which this operator, this differential operator, doesn't see. Okay, so it's possible to find some spatial distributions of u, right, such that when you take the first derivative, multiply by e, multiply by a, and then take another derivative, at the end of the day you get a 0. Okay, so these are referred to as homogeneous solutions, meaning non-trivial solutions to this differential equation, right, to this differential operator, which is subject to no boundary conditions or no forcing. Okay, and then particular solution, right? And so basically what you do is you derive this once and for all, right? As you can see, it's independent of what forces you apply, what boundary conditions you apply, right? So that piece is always going to be there. Okay? And then you have a particular solution, right? And this is a little bit of an art. Okay? It's developed for every situation sort of that's given to you, right? And it's not concerned with finding that function, right, which vanishes, basically, on which the differential operator vanishes, but you just need a function, right, that will come out of this analysis that would satisfy the equation for a given forcing. Okay? And once you have these two pieces together, typically the homogeneous solutions come with undetermined coefficients, okay, as you recall from your differential equations class, right? And then these unknown coefficients, right, together with a particular solution that's added to the system are computed from the problem boundary conditions. So this is how the flow of this goes. Okay, so let's take an example. Okay, I just want you to go through this process once for sort of maybe a non-trivial example, right? And then I'll show you how this differential equation machinery is used to generate structural elements that can be programmed and used in codes. Okay. So example 1. Okay, and then we're on page 1.3. Actually, a very sort of typical example for the use of these truss type elements. Okay, I have a ceiling. Okay, and I'm going to take a flexible cable and I'm going to suspend it. Okay, the ceiling. Okay? There's a cable. So the problem of interest is cable under its own weight. Some applications with such things here and there. Right. All right. So now let me develop my coordinate system. So I'm going to start my x coordinate system as going this way. Because I don't want to introduce other variables like y and write things in terms of y. So let x go along the length of the cable, oriented like this. Okay. And then we know that this guy is going to be subjected, okay, to the force of gravity, right, where I can express the distributed load W, okay, directly in terms of the density of the material, rho, okay, density, in this case mass per unit volume, okay. So you tell me this is a steel cable, I'm going to use the density of steel, okay, at a given temperature, room temperature, for example, right? So then I need to know, right, mass per unit length, okay? The way I get mass per unit length, I take the density, right, mass per unit volume, and multiply by the cross-sectional area, rho A. So I have mass per unit length, okay? And then the gravity force per unit length, right, is going to be mass per unit length times what? Gravitational acceleration, g. Acceleration. Okay, so I'm going to assume a prismatic and finally, of course, very important, right, the dimension itself, I assume L, right? So you see everything is written symbolic here, right? So which means that you develop solutions for a fairly large class of cables. Okay? So if you can supply to me the density, the cross-sectional area, and the length, okay, gravitational acceleration is always a constant. 9.81 meter per second squared. Okay, you can't get around that one. Okay. Right. Then I can generate for you, hopefully, right, a displacement profile in the cable that satisfies, right, this loading condition and the boundary conditions. Okay, we'll talk about that a little bit later. Okay. So then Wx as a function of x becomes rho Ga. Okay, and for a prismatic bar, right, this guy is constant, so this is good. Okay, this example will also show you what do the displacement and force distributions in the bar look like for constant distributed loads. Okay, right? Then the differential equation looks like this: EA, as I said, prismatic, right? D squared U dx squared equals to minus W, which is minus rho G A, like this, right? Okay, so then I can go ahead and divide through by EA. A's go away, right? E comes here. So what is the first thing you observe, right? Is if I suspend the cable with one cross section, okay, made of steel, for example, or any other material, and then next to it I suspend the cable of the same length, made of the same material, but with a completely different cross section, right? The detail of a cross-sectional area doesn't play a role. Both cables will displace by the same amount. Okay? I don't know if this is obvious to you, but comes out of this analysis quite naturally. Right? So then you simplify the problem a little bit and you solve d squared u dx squared equals minus rho g over E. Okay, right. So next, okay, homogeneous solution. Okay. Okay, so this guy looks interesting. So you're interested in computing d squared u dx squared equals to 0. Okay. Of course, if u equals to 0, right, that works. But, u equals to 1 works, right? And u equals to 2 works, and u equals to 15 million works, okay? So there's a general expression. Okay? So then, again, if you dust off your notes from ordinary differential equations, right, you find that for equations, right, second order like this, you look for solutions of the form u of x equals to c, right, some arbitrary constant, e, to some other arbitrary constant, r, times x. Okay? So c, r are constants. All right. So then if you compute the second derivative, okay, take this, plug it in, okay, you get c, r squared, right, e to the rx, okay? Equals to 0, okay? Good. So then you can go, right, r is a variable, e's cancel out, right, and you get r squared equals to 0, okay? This is referred to as the characteristic equation, right? So if r squared equals to 0, right, the characteristic equation has two roots, right, r1 and 2, both equal to 0, okay? So in that case, right, where we have a repeated root, then your u, and again, we're talking about homogeneous solution, right? So don't forget to put the h's here, h here, right? H here equals 2, right? Some constant c1, e to the r is 0, times x, right? Plus c2, right? Next term, x, and then e to the 0 times x. Okay? E to the 0 times x is 1. E to the 0 times x is 1, right? And you get c1 plus c2x. You see? So anything of the form like this, right, does not see, okay, but it doesn't see the differential operator. Okay? So whatever your solution is, you just go ahead and you can always add that component, okay? And that would satisfy the equation. Okay? So for this case, we developed a homogeneous solution. Okay, let's look for a particular solution. Right? So here you take UP and you write d squared dx squared UP of x, and now you look for a particular right-hand side, right? In this case, emanates from the gravity load, okay? Rho g over e. Okay? So then you're saying, look, you take in a function. That's where the art comes in. Okay, you take in a function, you take in its second derivative, okay, and you're getting a constant. Okay? So what would be a good candidate for a function like this? Okay? Well, it turns out that a quadratic monomial will work. Okay. So then if you assume your UP, right, as I said, this is where the art comes in, and you say, well, I'm going to make it look like this, rho g over e, put a 2 here, put x squared there, okay? You can easily check that you take a function like this, plug it back in here, you get the constant right-hand side. Okay. So then the general solution, okay, becomes ux equals to, you take the homogeneous part, c1 plus c2x, okay, and you subtract, and you add the particular part, right, that has a minus sign in front of it, rho g over 2e x squared, okay? So you're almost there, right? You use the differential equation, you use the load. What haven't you used, okay? You haven't used boundary conditions. Okay, so what do you know about boundary conditions? Here's your cable, okay? Right, here I have a location x equals to 0, right? And this is a location x equals to L, okay? Let's start with a simple one. At x equals to 0, clearly u of 0 must be 0, right? The cable is suspended. At that point, it cannot move, okay? So that's a done thing, right? Then, you apply the gravity load, the cable elongates. Okay? You look at this point here. Do you know how much it elongates by? You don't, okay? Because different cable will give you a different elongation. But what do you know? You're not putting any force here, right? So, which means that whatever solution you're going to generate, right, at the tip must produce exactly 0 force. So n of 0 equals to 0 here. Okay? And so the boundary conditions become one, u of 0 equals to 0. Okay? This is known as the kinematic or geometric. Right? It's nothing to do with the forces that you apply. You know that your structure is not going to move at that location. So you have to build that into the solution. Right? And you have another one that says n, not 0, of L equals to 0. Okay? This is the so-called static or force boundary condition. So I will use mostly kinematic and force. Okay? And so an important remark here is that once you go to the boundary, right, in this case it's just a point, and at that point you need to decide what it is that you're going to apply. Okay? And you can either apply kinematic, right, or force boundary conditions. You cannot do both at a given location, right, because it could give you an ill-posed problem. Okay? So it's an important part, right? For every boundary location, you can specify either kinematic or force boundary condition. Not both. Okay? And so then when you're setting up a problem, and this is where I see a lot of people struggle, This is a fairly simple case, right? But it gets more complicated, especially when we go into beam bending, right? You basically need to, right, visit every boundary point and ask yourself, do I know what the displacement is? Okay? If you know what the displacement is, you set it. Okay, say this is the boundary condition. If you don't know what the displacement is, you have to set the force. Okay? You have no choice. And you cannot set nothing. Okay? And you cannot set both. Okay, so then what do we know, right? If u of 0 equals to 0, right? It means, right, that if I look at this equation here, I plug in a 0 for x, I plug in a 0 for x squared, I get a 0. It means that C1 needs to be 0. Okay, there's no choice there. Okay, so I eliminated one constant. N of L equals to 0. Okay, implies what? Epsilon of L, right, times E, which is a stress, and then times A, which gives me the force, equals to 0. Both A and E are positive. I can divide through. Okay, do you see what I mean? And so now the force boundary condition translates into the strain boundary condition, right? And then I use the compatibility relationship that says du, right? Epsilon is du dx, right? Epsilon at L equals to 0, implication is du dx at L equals to 0. Okay? And so a force boundary condition ends up being a condition on the slope. Condition on the displacement derivative. So this is how the two are connected. Okay. All right. And so then if you crunch through the mass, you find that C2, right, minus rho G over E L equals to 0, right? The implication being is C2 equals to rho G L over E. Okay. And then you nail down the second constant, and you are done at this point. Right? Just need to put everything together. Right? So we have the constants, we have the general expression here. Right? So we can finally state the solution. U of x equals to rho G over E times L x minus x squared over 2. Okay. Right. So you see displacement has a quadratic profile. That's quadratic function. Okay. Now, what's of interest in structural analysis is not necessarily the displacement itself, okay, but you're interested in the distribution of stresses and forces. Okay? So then what is N? N of x, right, becomes, and here you just go back and you apply, right, the constitutive law followed by compatibility. So you get EA du dx. Okay, so then you take the relationship you just derived, okay, and differentiate with respect to x. So you get rho G A L minus x. Okay? And so while the displacement is distributed quadratically, right, the force undergoes a linear distribution. Linear profile. Okay, not so important now, but it'll become important later. Okay? Kind of understanding how displacements and forces distribute under different loading types. Okay. And so we can draw the displacement distribution. Right? So we start with, right, so this is u of x. Okay. We'll start at 0. X equals 0. Let's sample at halfway point, and let's sample at the end. All right. Get something distribution that looks like this. Right. Okay. So u equals 0. In the middle, u ends up being 3/8 rho g over e L squared, right? And at the end, it ends up being rho g L squared over 2e. Okay. So when you're designing cables, you see, so if I increase the length by a factor of 2, right, I'll increase the overall displacement by a factor of 4. Okay. It's interesting, came out of that analysis, right? If I reduce my Young's modulus, the stiffness, by a factor of 2, right, the displacement increases by a factor of 2. Okay, so it's interesting to see these things. Okay, all right, and so clearly you see that your solution satisfies the boundary condition. Right? Now, what about the distribution of the axial force? Right, again, let me draw the cable here. Right. This is, let's say, x equals to 0, x equals to L over 2, x equals to L. Right? And so if you examine this relationship here, clearly at x equals to L, n is 0. Okay. Then it goes all the way to, right? So n at L is 0. N at 0 becomes rho g AL, okay? So this is a maximum force that the cable will develop, and it's not surprising, right? The force will be in the location of where the cable is suspended. And in between, let's say halfway point, you get half the force. So L over 2 is rho G AL over 2, okay? And so this problem shows you how these differential equation type approaches give you everything you need to know about the problem. Okay. And so now that we've set up the problem, set up the differential equation, right, started to look at boundary conditions, constructing solutions, I think we're at a good point to talk about the concept of a stiffness matrix. Okay, stiffness matrix. Every time you talk about stiffness, everything you've seen, right? For now, you look at springs, for example. What is stiffness? It's a property of a spring, right, that relates displacement to force, right? And a linear spring, right, gives you a linear spring coefficient, K, right? So F equals K times X, for example, right? Where X is the amount of displacement and F is the force. What you'll see is in structural analysis, there's no longer one stiffness coefficient, okay? The stiffness will be expressed in terms of the matrix. Okay? And so what I'll do next is we'll develop that matrix. Okay? So stiffness matrix, right, for a bar truss element. Okay, so we are on page 16 now of the notes. Okay, all right. So let's see. So let's take a bar now. Okay, these are two end nodes. This guy is of size L. Okay. Right. And assume that we have some displacement, call it U2 here, and call it U1 here. Okay. And so what's interesting is to figure out what, right, the question I want to ask, right? What are the nodal forces? Nodal forces, okay, that result from arbitrary combination, right, of displacements U1 and U2. Okay? Right. So this is a linear differential equation, which means that a superposition principle applies, right? So for example, if I say U1, U2 is 0, okay? I apply some U1, I'm going to get a force, F1. Okay? Now, what do you mean by the force, right? There'll be a nodal force here, and there'll be a nodal force there, right? So for every U1 I apply, I'm going to get two forces, one at each node. Okay? Right? So then, when I apply U2 and restrain U1, I'm going to get another two set of forces. Okay? And so when I apply U1 and U2 simultaneously, I just add them, right, to get the nodal forces corresponding to the two. Right? Because it's a linear differential equation. In addition, right, if I restrain U2, right, instead of U1, I can just put a specific displacement, like 1, okay? I'm going to get some forces, okay? And then the actual forces corresponding to U1 will scale, right? So I need to take the result and multiply it by the magnitude of the displacement. And so all I need to do, right, is look at two cases. Right? U1 equals 1, U2 equals 0, right? And U1 equals 0, U2 equals 1, okay? So what this will do, right, the situation will go and give me two forces, okay, which I will call K11 okay, which will be the force at this node here, and it'll give me K12, right, which will be the force at this node there. K11, K, not 1, 2, I apologize, I'm going to call it 2, 1. Okay. This setup here produced for me a pair of forces that I would call K12 and K22. Okay. So let's explicitly compute those. Okay. And because we developed all this machinery, I'll go quickly. Okay. So case 1. Right. This is L. Okay. The properties are E and A, as before. Prismatic. U1 equals 1. Right. U2 equals 0. Okay. Right. So differential equation looks like this. EA d squared u dx squared equals to 0, right? There's no forces, only displacement boundary conditions, right? So we know this situation gives me u, right, homogeneous equals to C1 plus C2x, okay? Because there's no forcing, u particular is nothing, equals to 0. Okay, applying the boundary conditions, I know that u of 0 equals to 1, and u at L equals to 0, right, according to the setup here. okay, introducing the boundary conditions, right, into this equation here, gives me the following expression, right? U of x equals to 1 minus x over L. Okay. So what I see, right, is if this is my bar, this is x, right? This is x equals to 0, this is x equals to L, right? I'm going to have a linear displacement that starts at 1 and decays linearly to 0. Okay? Corresponding to this displacement, I have a force. N of x equals to E A du dx equals to EA times, right, du dx is what? Minus 1 over L, okay, equals minus EA over L. Okay? So what this means, right, is that the bar is under compression. Okay? Bar is under compression. It has a constant internal force of minus EA over L. Okay? Which means that the nodal forces corresponding to this compression, right, you just go to each edge and apply and take this number, multiply that by the corresponding normal, right? You have a force pointing in the negative direction with magnitude EA over L, right? You go here, you apply normal pointing in minus 1, right? You get a positive force, EA over L. Okay? And so this becomes, right, this is exactly K11, right? And this is exactly K21. So I record K11, K21 equals to EA over L, right, positive, and EA over L, negative. Okay, so by the way, you can see that the bar is in static equilibrium because you have on the left, you have a positive force, on the right you have negative, right, and their magnitudes are equal. So the bars go nowhere. Okay, so everything is in equilibrium. Right? Good. Right? So then let me focus on the second case, right, where U1 equals to 0 and then U2 equals to 1. Okay? And so going through the motions, right, what you find is the corresponding displacement distribution now looks like this. Okay? It's linear but facing the other way. This is 1. So basically U of x equals to x over L. Okay, that will solve that problem. Right? The corresponding forces, N of x, right, is EA du dx, okay, equals to EA over L, positive. Okay? So if I look at this bar, right, the bar, the force state inside the bar is tension. Okay? So, as I said, well, this was compression. Let me write this down. Right? Negative. Positive means tension. Right? Right? On the inside, you have a constant force of EA over L. Right? And then you go to the nodes. You take this guy, multiply by the unit outward normal. You get EA over L here, positive, and EA over L, negative. Okay? Right? And this is exactly K12 and K22. So K12, K22 equals to minus EA over L, EA over L. Okay? So for each unit of displacement, right, I found out a pair of forces that are given by these expressions here. Okay? So which means that for a general case, okay, general, every time I want to find forces, F1, F2, nodal. Okay, so this is my bar. I have U1, U2. I have the corresponding forces, F1, F2. Okay, the way I find F1 and F2, okay, is I take U1 and U2, right, and multiply by the matrix that is composed, right, of the column vectors that are computed before. Right? EA over L minus EA over L minus EA over L, EA over L. Okay? And so the object that emerges from this analysis is this 2x2 case, and this is exactly the stiffness matrix of a bar or truss element in local coordinates. Okay? Meaning the coordinates that are oriented on the x-axis. Okay? Right? So you see, we're basically use the power of differential equations and boundary conditions, right, to come up with this simple expression, okay, that relates. Okay, as input, you take the displacements. Okay, as the output, you get the forces, and because your displacements is now two-dimensional in this case, right, your force vector is also two-dimensional, right, and the only general object that in a linear fashion relates a two-dimensional vector with a two-dimensional vector is a 2x2 matrix. Okay, that's a stiffness matrix. And the way we derive the stiffness matrix, right, is we applied unity displacement, right, unique and unit displacement. Okay, and so this gives a definition of the stiffness matrix from the standpoint of structural analysis, okay, that says, right, that Kij, right, Ij, right, the Ij entry of the stiffness matrix right? Matrix, what is that? Is a force at degree of freedom, DOF, I, right? Due to what? A unique and unit displacement at degree of freedom J. Okay. So DOF here stands for degree of freedom. Okay. And so in our case, the degrees of freedom are what? Are displacements. Okay. To each one of those, we associate a force, right? And if we look at the structure of the matrix, right? For example, if I fix, if I look at this entry here, minus EA over L, right, is a force. So I equals to 1, right? J equals to 2, right? So it's a force at DOF 1, right, due to a unique and unit displacement of DOF 2. Okay. So that's what it comes out to be. But practically, okay, what we did, this is an important thing to note, is we used the differential equation machinery, okay, applied general displacement boundary conditions, right, solved for the displacement distribution, applied the constitutive law to get the force state, used the force state to extract the nodal forces, and recorded the nodal forces. And so that seemingly complicated process gave us a nice linear relationship between nodal forces and nodal displacements. Okay, and these are the kinds of things that we need in order to build up sort of element by element. Okay, our structural analysis framework. Okay, all right. So let me stop here. The next lecture will cover beam columns.